you for these overly kind words. It's a pleasure to be in Vienna. I just checked the weather forecast. This is the only sunshine we'll get this week. So, and I'm keeping you in here. I have to apologize. I put too much of detail into this talk. It's a mostly new talk, and I was overly ambitious, and you don't have to listen to all of it. You can interrupt me at any moment and ask me questions. Okay? By the way, this year, I always like to show a painting by William Turner. He came through Vienna. He never painted anything, but he took a lot of sketches. So this is from his sketchbook of Vienna. This is supposedly Stefan's. So what we're interested in my group, and we heard already, this is about stochastic processes, everything around Brownian or Fickian sometimes, as it's called when you talk about the linear scaling of the mean square displacement. We heard about the Gaussianity, and then we're mainly interested in what happens when we go to anomalous diffusion when this linear scaling of the mean square displacement. And later on, I will actually replace this anomalous diffusion index by the Hurst index. That's more for the audience. I will talk about non-Gaussianity, and we'll also talk about maybe non-ergodicity in the sense that time averages no longer converge to ensemble averages. The background is that we're interested in experiments and simulations where one can measure the whole trajectories of single particles. For instance, here you see these zigzag curves. These are actual measured trajectories of the end parts of chromosomes in living cells. Now, we heard about non-Gaussianity already. I want to spend only a few slides on this. And this is actually a field that has a lot of history. There's work by Walter Cobb in glassy systems. There's a lot of work by Steve Brownian. And I'll show you an example here from Yair Hochman's lab from Tel Aviv University. She's observing single particles, these shiny objects between obstacles. These are nanopillars that are seen from top. And depending on density of these nanopillars or disorder, you can see that the probability density function for displacements can actually have exponential tails. That's quite a widely observed phenomenon. So here is log versus so straight lines here in exponential. They don't occur all the time. You can see crossovers as function of time and so on. But this is one phenomenon I want to look at. Motivate, I show you one simple example of a protein. It's a mini protein, it's a very short protein, and it has a very shallow energy landscape. There's only very gentle dips in the landscape, so it can assume different conformations, but it can flip-flop between them. So it's constantly shape-shifting, and the same protein can assume all these different shapes. And when you look at the gyration radius, look at the gray curve, it's fluctuating quite a bit. And here you have very extended configuration. This, and you have a lot of. When it's very extended, it has a different hydrodynamic radius. So when I plot the time local diffusion coefficient on the same time axis, you see that it's very extended. It has a very low diffusivity. So this is a perfect example for me for a stochastic diffusivity. You don't have to care about the embedding space. I have another example. This is from the Nicodemus paper from a few years ago, where they assume that the environment is disordered, but it's changing on a timescale faster than the motion we observe. So we can consider the environment as annealed somewhere here. I think this you can see it. And when it's trying to move through this hydrogel, the hydrogel is moving, it's breathing. So sometimes it has a lot of space around the tracer, sometimes around it, and then this is just made up. But essentially, you would have again. Can we use this to model this kind of phenomenon? I should say this is only one of a lot of different models that people are using for this non-Gaussian processes. I want to show you quickly because I want to come back to that. So this is the normal Langevin equation, stochastic differential equation in the overdamped limit, as we heard before, for the position of the particle. This is noise psi. And Now I want to modulate my noise amplitude, the diffusion coefficient. And I want to do it as a stochastic process. It's constantly changing. The only requirement I have here is that it should be a stationary process. Then, of course, I choose the simplest one. I choose the Uhlenbeck process. I have a mapping in between. I use y squared because when I square a variable, it's always positive. The probability should be positive. You're laughing. It was a great trick. And that was actually invented by my old friend Igor Sokolov. So this, then, only with this trick, all of a sudden you can solve things exactly. Which is then my other friend, Alexei Chechkin, who wants to solve everything under this. Perfect. So what we did is then we combined this, and you see you have, in this Ornstein-Uhlenbeck process, you have a well-defined time scale. This is the realization time in the harmonic potential, and this is a crucial number in this. Now here I look at equilibrated initial conditions. So for each trajectory, I choose one initial value of the diffusion coefficient, but of course from the equilibrium distribution. And what happens then is that the mean square displacement, it grows linear in time, there's no crossover, it has the same when I divide by time, it has the same coefficient at all times. Always the equilibrated diffusion. Still, at short times, I see exactly exponential tails, and then after some time that is longer than this correlation, a Gaussian shape. I can see this crossover in the kurtosis. So the kurtosis, this is for one-dimensional system with dimensions. In one dimension, the exponential distribution has over, and for the calculations, we chose a tau value of exactly 1. So it crosses over exactly at correlation. We also looked at with Victoria, who used to be my PhD student 3 times. Thanks for inviting me. So with her, we looked at different distributions and also non-equilibrium. So this is all I wanted to say to this kind of Brownian. Now I want to get to long-range dependent kind of motion. We heard the word fractional Brownian motion already. And to motivate it, I use this result of a quite extended study of many different systems, from single molecule all the way to storks and vultures. We have time series of their trajectory. And then we classify them according to these scaling exponents given by Mandelbrot. I only want to look at it. When J is different from 1/2, it means the motion is long-range correlated. Can be positive, can be negative. So you can have values that are smaller than 1/2, values that are bigger than 1/2. But everywhere where you have a blue color here, this is really long range. So it occurs quite a bit in this system. We have different crossovers then also according to the observation. And I want to describe this by this fractional Brownian motion. And the background is actually, normally when we talk about physical systems, like the Gauss chain over here, we can solve them exactly by having a large number of coupled Markovian stochastic processes. And the coupling, of course, comes through these springs in the polymer. But in that case, we have fluctuation dissipation, and we know the system is equilibrated. I do not want to look at equilibrated systems. To really this fractional Brownian motion, which we can interpret as an open system. We talk about things that are alive here, and so on. So I should also say that if I go to the overdamped limit of this generalized Langevin equation, I get to the same structure of the correlation function. So what do I look at? Again, Langevin equation. This time, for now, it's a constant diffusion coefficient, and this is now Gaussian but long-range correlated noise, in the sense that I define noise correlated. This is a smoothing that was introduced by Mandelbrot, but that if you only go to tau different from 0, and then you can write it in this acid. You see here, this is the long-range correlation, H between 0 and 1. This is always decaying, but has a power law. But this guy and change sign. When h is smaller than 1/2, this is negative, and this means anti-correlation. In the chain, you give this monomer a kick to the right, so you tense the spring to the right, you expand the spring to the left, so it's being restored very quickly. So it's much more erratic. And this is what you also see here. Smaller than 1, when it's larger than 1, it's positive. And when I then calculate the normalized correlation function for this process, this is what it is. So it's something in the middle here, the central line. When h is 1/2, Brownian motion. The correlation goes from 1 to 0 within n size, and then stays 0. For super diffusion, it stays positive and has a very slow power law recovery. And when it's negative, when it's anti-correlated, you see it goes to negative values, and then slowly, also in power law, relaxes. And one of the main ingredients is that when you have subdiffusion, when you have this whole area under the correlation function, otherwise you violate things and you go back to normal diffusion. Very quickly, I can send you the slides if you like. I just want to show you an experimental example. What happens in a biological cell when you knock out all the action of activity, all the molecular motors are switched off. This is an example for this. Negative correlations, a viscoelastic system, and in this system, after you knock out, after some time, the cells recover and they have this correlated motion. That's, to my knowledge, one of the few examples where you really see both in the same system. Good. Is my old postdoc Jay Young is here as well. I show this one slide here. You remember this work? I mean, look at this. This is shocking, isn't it? So we looked at simulations in the Brownian group of crowded polymer membranes. So what you see is a bird's eye view of individual lipid molecules that make up the lipid bilayer, and then they crowd it with big chunky proteins. And in these crowded systems, we get very strong, very pronounced non-Gaussianity, where the scaling exponent is not too as in Gaussian, but it's varying somewhat. Only when it's in this dilute phase you get back to the Gaussian. And as in simulations, we can analyze the motion. It looks, this is the time local diffusivity that we get from individual trajectories of lipid molecules. In the dilute limit, it looks very nice, stationary, but in the crowded limit, you see there's a lot of kind of intermittency. So the diffusion coefficient is, again, fluctuating in time. You also see when you look at all the mean square displacements, the time averages of all the lipids in the dilute phase, they're all on top of each other, with no variation, whereas you get a big spread of amplitudes in this crowded. Now, can we do something similar, like this diffusing diffusivity? And I forgot to say something when I was talking about the Brownian limit. There's not only this one model I showed you, there's other kinds of formulations. They're different. Some people are using reflecting boundary conditions not to get negative diffusivity and so on. But the model is very stable. Whatever I put in, the results are stable. It's a nice C array. It's robust. Let's look at what happens when we include these correlations. So it's the same thing as before, just that now I use fractional Gaussian noise, long-range correlated noise in this Einstein. And then I add my Einstein-Uhlenbeck variations of the diffusion. And now it turns out it very much depends on the details of the model. Memory is not forgiving. We're in Vienna after all, right? So this is one example. I don't show you the two other examples. What is robust in the sense of all the models we looked at is this crossover from initial exponential tails to a Gaussian at long times. This is fine. But when you look at the details, even the mean square displacement is not unique. In this case, I show you here subdiffusion, because then you twist something about this area under the correlator. It's no longer zero. Diffusion crosses over to normal diffusion, whereas super diffusion stays super diffusion. Another bubbles, we have everything close to normal diffusion, and so on. I don't go into the details, but flavor of what's going on, and I don't have a good answer for it. We don't have, a direct way of projecting down these equations. And other examples now where similar questions are coming up. Also, what you see here, we have some effective diffusion coefficient, and jump where we have normal diffusion. So when we come from the two anomalous regimes, we don't meet at the same point. Of course, I should say this was done with my Italian friends. Alexei Chechkin was in Padua, Flavio Sena was involved. And this was supposed to be the first and simplest model. This is why it's called Prosecco. We never got to Vino, we never got to Gap. Maybe one day. Anyway, this was what happens when the diffusivity is not a constant. What happens when you interact with a wall? Now, it's a simple hard wall, but even here we have issues. Because when you have, let's say, a super diffusive particle, so it's persistent, it likes to go in the same direction, so it comes to the wall, and it's being reflected, but it still wants to continue. It's building up probability close to the wall, and this is what we see. It reminds of active particles, active Brownian particles close to walls. They like to stick. Here, of course, it's due to the persistence. And you see that the equilibrium distribution really has to be. So it's not as you would expect in an equilibrated system. The same amplitude everywhere. Increasing towards the bound. And the opposite is true when we have subdiffusion anticorrelated. And this, of course, is the Brownian limit that, fortunately for us, the simulations did exactly. Now you can say, you implemented your boundary conditions wrong. But let's go to something that is mimicking a box. Let's go to a quartic potential next to the 4 potential. For super diffusive fractional boundary. You see, the same effect is here. Here I don't have to define any boundary. We're pretty confident that this effect is here. But of course, the ideal way would be we start with a physical system, like we have a polymer chain, then we have a wall, and the wall should only be reflective for the central beam. Now, the whole polymer chain is moving towards the wall, and then, of course, there's interaction with that one beam, but the whole polymer is trying to still move towards the wall. We are trying, but it's so difficult to get statistics. It's not easy, but that was so far my only idea to look at this system more physical. But why did we ever start doing this? I have a collaborator at Santa Barbara who's a biologist, and he knows what fractional Brownian motion is. This is really big fun. So he approached me and Thomas Feuter at Missouri Roller, and what Schemantas is interested in is doing brains. So he's slicing brains, and he's interested in the growth of certain fibers. They're called serotonergic fibers. They're very thin, and that's an example of a mouse brain. So this is when you smooth it, you see that the density is much higher when you're close to the skull, to a hard boundary. That's kind of a general theme of his research. So when we use this super diffusive fractional Brownian motion, like here, we can kind of mimic this density. Of course, for normal Brownian motion, there's no density. Now, why would we consider something like this at all? And this is just a general new way of to model polymers. So instead of having a regular random walk chain, we now have a chain that consists of persistent kind of segments. There's a tendency to go in the same direction. And this is then shown here. These are simulations of individual trajectories. A little bit of fantasy, you see some similarities here. And the funny thing is, it can also reproduce the full three-dimensional slices that they get from staining and so on. Now his big dream is, it's not only these serotonergic fibers, it's many more brain fibers, and now we want to get back to the physics. Now we try to have one of these growing random walks, and then they excrete kind of chemicals, and then in this field the others are growing. So we have and hopefully come back to this. This is just dabbling. It's beautiful, right? And I was able to hold a human brain donated to science. So that's quite, as a theorist, this is an adventure. Let me finish this part. Do I still have any time at all? Because I want to get to finish very quickly with a system that contradicts everything I said so far. So this is a system analyzed in the lab of my Potsdam colleague Karsten Beta. So they're looking a lot at amoeba cells that move in labyrinths, that move on surfaces. And here they have another experiment. Here the amoeba cells are more or less stuck on the surface, but they move colloidal particles. So they sit there and they're moving their little tentacles, and then they're moving colloidal particles, and they measure the trajectory. And the funny thing is that in this system, we never have a Gaussian distribution, but there seems to be a convergence towards exponential tails. That's the longest time scale they can observe. This is roughly half an hour. After that, all cells divide and is mess. But of course, there's one thing we have. Not all cells are the same. So even when you look at the mobility of single cells in these systems, exponential tails. But here, kind of you might think a lot of cells work together to move these colloidal particles, so there's an averaging out of the effect. I don't fully understand what is going on there, but it seems that at least within the lifetime of the experiment, we are converging towards. By the way, at shorter times, there are positive correlations. If I had 5 minutes or so, I want to go to even more question marks. So I expose you to all my question marks that I have at the moment. And my main message is fractional Brownian motion. It looks so simple, so innocent, right? You have this Gaussian equation. You have Gaussian noise, what can happen? Once you really need to calculate this is a terrible process. So now I want to ask the question, what happens if I want to make my scaling exponent time dependent? There can be many examples why I'm interested in that. I want to use it to describe motion in cells, but the cells, the meshwork inside the cells, it's changing all the time as a function of time. It's denser, it's falling apart, whatnot. Financial markets are changing H all the time. Here, this is a very naughty way of talking about financial mathematicians. Don't try to understand that. You see that the volatility, the roughness of the fluctuations is changing. So there's systematic changes in it. Or you go to membranes, you change temperature, you have phase transitions, alpha changes. Let me describe something. Then I ask my mathematical friends, and they tell me, oh, this is known in mathematics. It's called multifractional Brownian motion, which in principle is a nice idea. It's defined in a different way than what I described. About the t here, when alpha is a constant here, this is the increment of Brownian motion. Then I integrate, normally Mandelbrot defined it from minus infinity. The zero is actually due to Levy. So this is more a physicsy kind of thing. We start at zero with initial conditions at t. And then I integrate this with this power law kernel to give me fractional Brownian. Now I introduce a time-dependent alpha. And in these models in multifractional Brownian motion, it's alpha of t. Only the upper integration limit. It's not dependent on the integration variable s. And the effect is when you calculate, for instance, your mean square displacement, it only depends on alpha of t. It forgets about the memory. I'll show you why even in a simpler thing, this cannot be true. Let's look at a Brownian motion that changes from one diffusion coefficient to another. I can describe it like this, and when you look at the result, you see that it's immediately clear. When I'm below the switching time from one to the other diffusion process, of course it only knows the first. But when I already am in the second, I have a contribution from the first until the switching time. I can't have something like this in a system where I keep track of the motion all the time. And so when I correct for this, and now I make it dependent on the integration variable, you see that, for instance, what happens to the mean square displacement, these are exact results, but when before the switching time, of course, it only depends. After the switching time, it has a complicated mixture of alpha 1. If I go to the long time limit, I get alpha 1 minus 1 as one exponent, and alpha 2 as the second. And now it depends which one is bigger. So I can get cases, as I show here, when my old multifractional Brownian motion definition immediately switches down to the new exponent. Our new definition actually keeps the memory, and it goes with old exponent minus 1. So the memory is quite persistent. Is this the true physics? It's a nice mathematical model. I can't tell you more. But it would be really interesting to see experiments being done. Define response functions. You can also define it differently, like mixtures, and then the behavior is quite different. One more thing. Now we have something that depends on the trajectory time. Actually, one for our brain modeling is what happens when it switches as a function of space. So let's say we have one alpha in a given region, we have another alpha. And now you see that it's actually very important that we know what we do. Again, memory is deceiving. In this case, when it's super diffusive in the center, you see that normal fractional Brownian motion, the mixed definition, they more or less concentrate in the middle. Whereas with a full memory, they escape from the middle. And this is at least a more physical picture. It normally goes away from the large diffusivity. And the opposite is true in this case. So I just leave it here. Lots of questions with fractional Brownian. Lots of things to do, especially for the young people. But slightly worrying question, where's the physics? This is something we're trying to do, so hopefully next time you hear me talk about this, I can tell you a bit more. And let me quickly summarize. Single particle tracking so that we can analyze and try to understand. And in many cases, long-range correlated motion is identified as what's driving the motion. We have inhomogeneities of the environment that cause non-Gaussian displacements, both for Brownian motion, for I showed you peculiar interactions with boundaries. I showed you first approaches to warn you, I showed this autocorrelation function as the identifier for fractional Brownian motion. One should be more careful. You need to look at other quantities as well. Because I can show you that in several systems you get essentially the same anti-correlation relaxation behavior. You will not be able to tell it apart from what happens on an infinite percolation cluster. So, a word of caution, you need to know more about the system. I also didn't talk about data analysis methods that we've been working on more recently. And here, and I'm happy to